All right, ladies and gentlemen, welcome back to another video with Mr. Kenton in AP Chemistry. We're continuing our discussion and learning on kinetics, and today we're going to be looking at reaction energy profiles, which is essentially a fancy way of saying we're looking at graphs that are showing the energies of our reactants and our products and the things that happen in between, right? So it's a really useful tool, something that can help us understand the energy of the entire process, and things like that. So let's go ahead and get into this by looking at some information here that's going to help kind of ground us in this. So a reaction energy profile, what it is, it's a graphical representation of a reaction's potential energy versus the progress of the reaction, right? So you can notice that on your y-axis, you can see there that you've got your potential energy. So that's on your y-axis. And then on the x-axis, you've got your reaction coordinate. And that's essentially saying at different points within the reaction, right? So here at the reactants, that's where you're starting, right? And then as you proceed, you're going to proceed to products. Energy changes are going to happen. And then as you get down here where your products are, you're going to be at the end of your process. And certainly you could go in the opposite direction because you'd be reversing the reaction coordinate. Right? So essentially, you're going to have a graph where potential energy is on the y-axis, and essentially the progress of the reaction is on the x-axis. Okay? So it should be pretty straightforward. Now, on this, we also need to understand some things about what's going on with activation energy. And again, that should remind us of what we talked about in 5.5 when we talked about the collision model, that we know that molecules have to possess a minimum amount of energy to react. And, Arrhenius, he understood this, and he understood that molecules had to possess that minimum amount of energy to react, but he kind of wondered, why is that the case? Why do we need that activation energy? Why do we need that minimum energy? Well, first thing, in order to form products, bonds have to be broken in the reactants. Now, because bonds have to be broken, that means that requires energy. Without a sufficient amount of energy, you can't break a bond. So that's kind of point number one as to why we need that minimum amount of energy. We need to be able to break bonds. The second thing is that we need to consider is that when molecules are moving too slowly, or if they have too little kinetic energy, they don't react when they collide, right? So that's another component. So we know bond breakage requires energy, but we also know that if we have collisions that don't have enough energy associated with them, we don't get product formation. So that's kind of the second reason why we need that minimum amount of energy needed to react. Now, as we've defined already, activation energy E sub A is the minimum energy required to initiate a chemical reaction. Now, on our graph, if you're looking over here at what's going on to the right, activation energy, or E sub A, is going to be represented by that red line that goes from the reactant's energy to the peak of our curve, right? And on the peak of our curve, what we're going to have is what's known as the activated complex, right? And actually, I think, changing the color here, we can just write this over here, right? At the peak here, this would be the activated complex, or the AC, right? Now, your activated complex, or your transition state, is always going to be at the highest energy point on your graph. And so certainly the energy of the activated complex or transition state would go from the peak all the way to the bottom of the reaction coordinate. The energy of your reactants would go from this point here all the way to the bottom of the reaction coordinate. And so if we wanted to determine the activation energy from a graph like this, then what we would need to do is simply take the energy of the transition state, or our activated complex, whichever term you want to use, minus the energy of the reactants. And if you take the difference there, that would give you your activation energy for your forward process, right? And so I'll just say that this is activation energy EA forward. right? You could determine the activation energy of the reverse process, except it would be the transition state minus the energy of the products, and that would be EA reverse. Now, one last thing to note is that based on the reaction that you're looking at, you're going to have different activation energies. The activation energy, it isn't this like silver bullet for all reactions that they all have the same activation energy. Different processes are going to require more or less energy for them to take place. So just understand that it's going to vary from reaction to reaction. All right, a little bit more on activation energy, right? And so we're actually going to plot out what's going on a reaction energy profile with methyl isonitrile. So we look at this process, we've got CH3, and it's currently attached to nitrogen with a triple bond to a carbon, where the carbon and nitrogen are sharing their bond. Well, it's going to rearrange itself. There's a process in which it's going to rearrange itself to where eventually we're going to get it so that the carbon and carbon are bonded together and the nitrogen's on the outside with a lone pair. But in order to get to that point, essentially what has to happen is this bond has to break and the molecule has to rotate so that it's perpendicular to this carbon and this carbon-hydrogen group that's right here. Now, that's exactly what this text is really communicating here, is that the bond is going to break between carbon and nitrogen, the single bond specifically, and then the nitrogen-carbon is going to continue to twist or rotate until it's perpendicular to the H3C portion. Now, this particular component right here that I've circled in yellow, that is our activated complex. That is our transition state, right? That would be what we would anticipate seeing if we were able to look at this molecule as it's progressing. That's what we would see at the hill of our energy profile. And so certainly the energy to get to that twist and break the bond to where it's perpendicular, that's our activation energy. And then the reaction is going to proceed. It's going to continue to rotate until that carbon-carbon bond is formed, and then the energy is going to level off, and that's going to give us the energy of our products. Now, it's one thing for me to talk about this and to say it out loud. I think the next slide is going to have a graph that has some images that are kind of documenting the steps of the process that I think are going to make this pretty clear. So let's take a look at that, right? So here is our process, right? And so when we're looking at this, we could think of this as there are different snapshots that they're kind of zooming in on during this process, right? So this bottom left circle, this would be step number 1. This is when you've got just your reactants and you've got the carbon-nitrogen single bond with that triple bond to the other carbon, right? Now, so there's our energy. Kind of this arrow right here would represent the energy of the products, or excuse me, this is E reactants. We'll just say that that's E react, right? And as we proceed, as energy is being input or as the molecules are moving, what we start to see in step 2 is what's in this bullet that's right here. So that was step 2. And so we start to see that instead of it being a linear arrangement, we're starting to see that it's becoming bent, right? So it's going to start to put strain on that bond that's right here. All right. Now, when we get up to the top, right, we get to our activated complex. So that's going to be this spot right here. That's number 3. Okay, and so there's our activated complex. And if you're thinking about this, I'm going to kind of draw it to the side. It's going to be slightly off center, so just kind of bear with me. But if we go all the way down here, the black line would represent my energy of my activated complex or my transition state. Now, this next bubble, this is number 4. Notice here now that we've formed the bond between carbon and carbon, but it's still bent. There's still some strain that's on this molecule because it's not back to that linear configuration yet. And so then it's going to proceed. We're finally going to get to products, and that's going to be bubble number 5 here. And then that's going to give us, it's linear, carbon-carbon bond. It's at our lowest energy state. And just for reference, this little black arrow would be the energy of the products, right? Now, if you're looking at everything, maybe it got a little too busy for you, but you've got the blue EA arrow. That's going to be the difference between the energy. So EA is equal to energy of the activated complex minus the energy of the reactants, like we've drawn here. And hopefully that makes sense. Hopefully seeing that kind of visually helps provide you the context of what we were talking about just then. All right. Now, as you're looking at these reaction energy profiles, we can come up with the overall energy change that happens in that process, which is what we're going to call the enthalpy of the reaction. And so the enthalpy of the reaction, delta H, is going to be the potential energy difference between the products and the reactants. Okay, and so if you're looking at kind of the graph here, you would take the difference between products minus reactants. So you'd get delta H equals energy of the products minus energy of the reactants. Now, there's some possibilities here. A process can overall be endothermic or exothermic. And so if we have a positive delta H value, so if the energy of the products is greater than the energy of the reactants, then you're going to end up with a positive delta H value. So that means that energy was absorbed and the products have more energy, and we'd call that endothermic. If it's exothermic, that means that energy was released. So that means that the products were lower in energy than the reactants. So that would give us a negative delta H value. Now, looking at the graph that's been listed here, that's an example of an exothermic process. We can see that the products are lower in energy than the reactants. So if we took the difference between those two, we would end up with a negative value. Okay, and so that could be a task that you might be asked to do, is that, okay, given this reaction energy profile, identify what's the change in energy, what's the change in enthalpy, and is this process endothermic or exothermic? And to be able to explain that, I think that's something that you guys should be able to do. All right, the last thing that we'll need to take a look at, I guess, here before we move into using the Arrhenius equation, if you wanted to find the enthalpy of the reverse reaction, so you could do that, you would say, all right, energy of the reactants minus energy of the products. I think it's also important to note that if you wanted the activation energy for the reverse process, so if you wanted the activation energy for the reverse process, it would simply be the energy of the activated complex minus the energy of the products, and that would give you your energy, your activation energy for the reverse process. All right. Now, when we think about enthalpy and overall energy changes, something that we need to consider is that the value of K accounts for all changes in reaction rate except for concentration. This is going to include temperature and the presence of a catalyst. Now, catalysts, we'll discuss them much later, but for now, what we need to understand is that a catalyst is going to work by lowering the activation energy. So it's going to decrease the hill that your reactants have to climb in order to go to products. All right, and we can see that working itself out in this bottom right-hand graph, right? You have the red curve shows the reaction without an enzyme. And as you can see, the energy requirement is pretty steep, right? It's a much steeper hill. But then if you add an enzyme or if you add a catalyst, right, what we see is that the hill much shorter, and so it can proceed to products. And it's labeled, here's the activation energy with the enzyme, there's the activation energy without the enzyme. It is important to note that when you add a catalyst, regardless of whether it's catalyzed or uncatalyzed, the overall energy change, delta H, is not impacted by adding a catalyst. Okay? So, let me repeat that. Adding a catalyst does not change the enthalpy or the change in enthalpy of the overall process. The change in energy is still the same, right? You still went from reactants to products regardless of what the energy, activation energy was. So reactants and products are still at the same spot. Their energies didn't change. What does change, however, in our catalyst is the energy of our activated complex, right? Our activated complex without the enzyme significantly higher than our activated complex where an enzyme was added. Now, this other graph that's over here, you got collisions and energy. We know from our understanding of collision theory that changes in temperature and kinetic molecular theory are also going to be related to changes in kinetic energy, right? Because temperature is a measure of average kinetic energy. So if we increase the temperature, we're going to change the kinetic energy to some degree. Now, the only change that's going to have is it's going to cause more particles to have the energy required for activation, right? And so if you're looking at these curves here, kind of this T3, this curve that's a little bit longer and it's more distributed, that's going to have more particles that meet that activation energy requirement. Whereas your blue and your red curves, because they're at lower temperatures, you have less particles that have that minimum energy. All right. Last two slides. So then the last thing here is the Arrhenius equation. And please keep in mind, this is not something that you're probably going to be asked to do on the AP exam. It's not on the reference sheet. But it's just, if you're curious about how we could figure out activation energy, this is how we would do it, right? Because we've recognized K is dependent on temperature to some degree, right? When temperature changes, K changes. And so we've got it set up. It's in our lovely slope-intercept form, right? ln of K is Y. Negative EA over R is M. 1 over T is X, plus ln of A is our B. So we've got our slope-intercept form that we've seen previously. Now, K is our rate constant. EA is your activation energy in kilojoules per mole. R is the ideal gas constant. Now, it is important here because we're dealing with the ideal gas law, because we're dealing with kilojoules per mole for activation energy. You're going to want to use the 8.314 joules per mole Kelvin. That's going to be the R value you're going to need to use in order to solve problems like this, because if you try to use the other gas constants, the units aren't going to cancel out. Temperature is typically provided in Kelvin here. If it's not, convert it. And then A is a frequency factor. It's a constant that indicates the number of collisions that have the correct orientation to lead to products. You won't have to worry about A. Any information regarding A will either be provided to you, or when you solve a problem using it, is going to be removed from the equation, right? And so as you can see here, we've got Y equals mx plus b, so we've got it in that slope-intercept form, and I guess in this case it needs to be negative, right? But we could just simply plug in our information and put it in the calculator and get the slope of our line, right? Because if we do that, then we're going to see that the slope of that plot is going to give us the activation energy over our gas constant. And so if we know the slope, we know the R value, we can solve for the activation energy. Okay. And so that's going to wrap up this particular video. Think about where we've been, right? We talked about reaction energy profiles. It's a way for us to plot the energy of the reactants and products with respect to time in our reaction. We can use that information to find out what's the activation energy for a reaction by taking the difference in the energy of the activated complex and the energy of the reactants. We looked at how we could figure out overall energy changes with enthalpy by looking at the difference between the energy of the reactants, or excuse me, the energy of the products minus the energy of the reactants. Said how if it's endothermic, it means it has a positive enthalpy. If it's exothermic, it has a negative enthalpy. And then we looked at the role a catalyst can play in activation energy, how a catalyst is going to lower activation energy and the energy of the activated complex, but it keeps the enthalpy change for the overall process the same. And then we've looked at the Arrhenius equation, which can help us determine activation energy. If we've been given graphical data, we can use the slope-intercept form, and we can use that information to solve for the activation energy. I hope this video was insightful, ladies and gentlemen. If you do have questions, fill out the Google form, ask your questions in class, and I look forward to seeing you guys again soon. Take care.